Welcome to this session. In this session, we continue to give more examples on types of matrices. So we start by skew symmetric matrix. So let's give the definition. So this is a matrix. A square matrix which satisfies the conditions one, that Aij is equals to negative Aji for all I and j, all values. So this to mean that A transpose is the same as negative A if you're referring to the matrix A. And then number two, all the principal diagonal entries are zeros. So this is what specifies a skew symmetric matrix, a square matrix, which satisfies these two conditions. One, that the transpose of the matrix is equal to the negative of the same matrix, and all the principal diagonal entries are zeros. So examples. If I have a matrix A given by 0 minus A, 0, then this is a skew symmetric matrix because all the elements along the main diagonal are 0. That's the first condition. Second condition, if I give a transpose, then I'll get 0 minus A, 0, which is the same thing as writing factor out negative 0 minus A, and then A, and then 0. So multiply this -1 by every element here to get back the transpose. And you see this is the definition of the matrix A. So this implies that A transpose is equal to the negative of A. And since all the elements along the main diagonal are 0, therefore this is a skew symmetric matrix. B, if I have 0, negative H, negative G, H 0 minus F, G F 0. So you have to check for two things. One, all the elements along the main diagonal are 0, and then the transpose of the matrix is equal to the negative of the matrix itself. Now here B transpose is 0 minus H minus G, and then H 0 minus F, and then G F 0. If you try to factor out the negative, so this will be equals to negative 0. So you need to put negative H, negative G, H 0, negative F, G F 0. Because when multiply this -1 by this elements here, you get back our transpose. And you see, this is the definition of the matrix B itself. So this is B multiplied by -1. So this is what it implies. So since the transpose is the same as negative of the matrix itself, and the main diagonal, all the elements are 0, then this is a skew symmetric matrix. And then you can even say C 0, 0, 0, 2 minus 2, 5 minus 5, 6 minus 6 is skew symmetric because the first thing is a square matrix and all the elements along the main diagonal are zeros. And then if you get the transpose of this matrix, you get 2, 0, 2, 5, minus 2, 0, minus 6, minus 5, 6, 0. And you can factor out -1, and so the same as 0, 2, 5, minus 2, 0, minus 6, 5, and then this will be 6, and then here we have 0. So we need to have a negative here, so that -1 times -5 gives us +5. And you see, this is what defines C. So it means that the transpose of C is the same as -C. And this is one of the conditions that should be satisfied for skew symmetric. And since already all these elements along the main diagonal are zeros, then this is skew symmetric. And then let's define number 10, what we call triangular matrix. Now consider this matrix. If this is A, so we have A11, A12, A13, up to A1n. And then we have A21, A22, A23, up to A2n, A2, A31, A32, A33, up to A3n. This is an n by n matrix, so this would be AN1, AN2, AN3, up to ANN. So we want to use this matrix to define what we call an upper triangular and lower triangular matrix. So this is our main diagonal. So you see in this matrix, every element is of the form Aij, where I specify the row, J specify the column where the element lies. Now, so in this, if we have this as our boundary, the main diagonal, then here 1, 2, this 1 is less than 2, 1 is less than 3, 1 is less than n, 2 is less than 3. So in this region here, I is always less than j. But in this other region here, 2, 1, so 2 is greater than 1, 3 is greater than 1, 3 greater than 2, n greater than 1, etc. So here, all i's are always greater than j's. So a square matrix A given by A I J, and this is a matrix of order n by n, is said to be upper triangular if A I J equals to 0 for all I. Now, upper triangular means now everything below the main diagonal is 0. So for all I greater than J. And lower triangular if Aij is equals to 0 for all I strictly less than j. This position, everything should be so. When everything here is 0, then we call the matrix lower triangular. And when everything below the main diagonal is 0, and at least we have non-zero elements in this upper part of the main diagonal, then we call it an upper triangular matrix. So i.e., we say that a square matrix whose all elements below the leading diagonal are 0, is called an upper triangular matrix. E.g., if we have this, so we have A11, A22, A33, up to ANN, they're saying that a square matrix whose all elements below the leading diagonal. So all these elements, everything is 0, but at least we have these other positions. You may have at least a non-zero element here, then this is an upper triangular. So this is a general form, or you can say then if I have 2, 1, 8, 0, 4, 8, 0, 0, 5. This is an upper triangular matrix because if you identify the main diagonal, this is our main diagonal, everything below it is all the elements are zeros. So this is an upper triangular matrix. Or you can give we say 2, 0, 5, 0, 0, 8, 5, 0, 0. This is still upper triangular because all the elements below the main diagonal are zeros. So that's really what matters. All the elements below the main diagonal to be zero. So this is still upper triangular. Or you can say 2, 0, 8, 0, 4, 0. Even put here 0, 0, 0. Once you write this as your main diagonal, then you see that everything below the main diagonal is 0. So this qualifies to be called an upper triangular matrix. And a square matrix A is called a lower triangular matrix if all the elements above the principal diagonal are 0 or say zeros. E.g., if this is A, so say A11, A12, A22, A33, up to ANN. So when, so this have some elements here. If everything here is 0, when this is the main diagonal, then this is called a lower triangular matrix. Or you can, that's the general case, or you can be more specific and say, like if you have 2, 0, 0, 4, 8, 0, 5, 1, 3. This is an upper triangle, lower triangular matrix because once you identify this our main diagonal, elements above the main diagonal are 0. 2, 0, 0, 0, 0, 4, 0, 0, 0. This still a lower triangular matrix, can as well be called a lower triangular matrix, keeping in mind that everything above the main diagonal are zeros. And similarly, this you can say this is also upper triangular because every element below the main diagonal are zeros. So this specific example is both upper and lower triangular. And a matrix which is both lower and upper triangular matrix is simply a diagonal matrix. So this is diagonal matrix. So generally, so we say that a triangular matrix is any matrix that is either lower or upper triangular or both. So any matrix that is either lower triangular called triangular matrix, upper triangular, or both lower and upper triangular. And a matrix which is both lower and upper triangular can as well be described as a diagonal matrix. So in the next session, we'll give the definition of an orthogonal matrix and unitary matrix. Thank you.